next speaker is Professor Antoine Georges of Collège de France and École Polytechnique, and now I see it's University in Geneva also. You know, it's a large end limit of institutions. But he'll be telling us about strong correlations from Hund's rule coupling.
Okay, thank you, Ravin. And well, first of all, I would like to say that it's a real pleasure and a real honor to be there for the birthday of Ramakrishnan. I'll tell you a bit later what I owe to Rama, and that's a lot. Okay, so I've tried to summarize the main message of my talk here. So as you see, basically what I'm going to tell you about is that very often in the field of strong correlation physics, you hear a lot about the Hubbard U, okay? But actually, Hubbard U is very important, as the song says. But actually, there is a coupling which is, in my opinion, also extremely important and shows, and is very influential to explain the properties of a whole class of correlated materials, and that's the Hund's coupling J. Okay? So, in plain English, the message of the talk is that there is really a large class of materials, and this large class of materials encompasses transition metal oxides of the 4D series particularly, as well as, quite likely, quite a few of the iron pnictides superconductors, which are best characterized as Hund's metals. And these metals are strongly correlated not because they are close to any mod transition, but because the Hund's coupling is actually responsible for these strong correlations. Okay, so now that's the message. Those of you who want to take a nap can do that now. And I'm going to enter into the details of what I want to say really. Okay, first of all, I'd like to say that this whole talk is based mainly on 2 and actually 3 papers which have to do with the influence of the Hund's rule coupling. One is about sort of a general view on this problem. Another one is about strontium ruthenate, and there is one on the web about a radioactive material, strontium technetium oxide, which I'm going to tell you a bit about later. And there is a bunch of very young, very talented young people here who have been the main leaders of this research effort, who are listed all the bands. And as you could guess, I'm going to show you results for these model calculations that have been obtained with dynamical mean field theory. Okay, so these are three plots which plot the quasi-particle weight versus the strength of the Hubbard U normalized to half bandwidth, okay, for 3 different cases, 1 electron in these 3 orbitals, 2 electrons and 3 electrons, the half-filled shell. And these different colors of the lines correspond to different value of the ratio of the Hund's coupling to U, okay? So different J over U. So I want perhaps to start by this plot, which is the half-filled shell. 3 electrons in 3 orbitals. That would be relevant, for example, to strontium manganese O3, okay? And you should observe here that we have a Mott or Boyton-Rice Mott transition at a certain critical value of U when J is 0, that's the black line here, and when we increase the Hund's coupling, the critical U is pushed downwards quite efficiently. So the critical U for the Mott transition is lowered by the Hund's coupling, and this is something that has been known for ages. Ages meaning a decade and a half, something like this, in various contexts, starting with simple Gutzwiller calculations and then DMFT and so on, and that's quite well known, okay? So for a half-filled shell, the Hund's coupling is very efficient in reducing the critical U of the Mott transition, so it correlates the system more, okay? Now please go to this case here, which is 1 electron in 3 orbitals. You observe exactly the opposite phenomenon. Namely here, the Hund's coupling is actually increasing the critical U for the Mott transition. And this is something that is here and there in a couple of older papers, but has not been very, very well emphasized. And it all can be explained extremely simply in terms of looking at atomic states, I will do that in a few slides. So I will explain why this happened and why this happens. And in fact, more importantly, this is the generic situation. If you take 2 electrons in this 3-orbital shell, then you also see that the critical U for the Mott transition is increased. In fact, this is the peculiar case. It's only in the case of a half-filled shell that the Hund's coupling J reduces critical U. If you are in a non-half-filled shell, the Hund's coupling actually increases critical U. So you could think, okay, well, this means that the Hund's coupling always decorrelates the system. It makes the system further away from the Mott transition, and so the system is less correlated. And actually, this is true in the case of 1 electron or 1 hole in this shell. But now you should look at this plot here. You will notice that for 2 electrons in 3 orbitals, and actually that's the generic behavior for any number of electrons in a shell with m orbitals, except when you are half-filled or when you have a single electron or hole, this is what happens. So this is generic, okay? You see that indeed the critical U was enhanced, but the quasi-particle weight in the metallic regime is strongly suppressed by the influence of the Hund's coupling. So really, in this case, you see that the Hund's coupling has 2 phases. It has completely antagonistic behavior, action. On one hand, it increases the critical U. On the other hand, it strongly suppresses the coherent scale of the metal. And you see that for reasonable values, quite appropriate for oxides, J over U of about 0.3, which is something which is very common in this 3D or 4D oxides, you see what happens. In order to match these 2 antagonistic behavior, the quasi-particle spectral weight as a function of U must have this huge plateau, okay, which connects the small values in the metal to this critical point, which is far away here. So what happens is that you open a wide region of coupling where the quasi-particle spectral weight can be quite small, 0.2, 0.1, while being very far away from the Mott transition. Okay, so these are the Hund's metals I'm going to talk about. Okay, so just to put this in pictorial form, you could say that the Hund's coupling in those cases, and this is the generic case, as we call it a Janus-phased effect. Janus is not a physicist, okay? He's actually a god, the Latin god of beginnings and transitions, and for this reason he has 2 phases, one looking ahead and one looking behind, okay? So this is what happens with the Hund's coupling. It has 2 phases. One of its phase decorrelates and the other phase correlates the system, okay? Okay, this nice statue here also illustrates the weakness and the inferiority of Western gods as compared to Indian gods, you know, because you have many more faces, but I think in our pantheon, even going to the Latins, we only have 2 at most. The Latins borrowed their gods from the Greek mainly, okay, but they borrowed everywhere. They apparently didn't borrow Brahma. Big mistake. Okay. So in the next talk, maybe a few years from now, I'll find an effect with 4 faces, but I only have 2 in this one. Okay. So now I've converted the results that I just showed you into a nice color plot, which goes well into fancy journals, okay? And please ignore the materials on this plot right now. These are still model results. Just look at the axis here. Here we have U over D, okay, the coupling strength. And here we have the filling of the shell, still the 3-orbital model from 0 to 6, right? And what is depicted here, the red bars, the black bars here indicate where the Mott transition takes place. So you see that this plot has been done for a specific J over U. This is in the presence of the Hund's coupling. So you see this effect that the filling which is the most prone to the Mott transition is the half-filled shell. Okay? And all the other ones are not so prone to the Mott transition. Okay? And what's depicted in color is a color intensity map of the quasi-particle spectral weight. Okay? So dark means very weakly correlated metal. Okay? And the lighter you are, the more strongly correlated you are. Maybe you'd prefer a different color code, but that's what we picked. Okay. So you see this effect that I was mentioning, that for 2 electrons in 3 orbitals or 4 electrons in 3 orbitals, you open this very wide region here, okay, where you have bad metallic behavior with very low quasi-particle weight, and you can have that while being very far from the mod transition. Okay, so that's the main message of the talk. And actually this was anticipated in really two very nice pioneering papers, one by Philippe Werner and co-workers who called this regime spin freezing, okay? And they didn't really put this in perspective in this way, but they did discover this phenomenon that the system was extremely strongly correlated in this regime, okay? It eventually makes its way to a Fermi liquid at very low energy, but only at very low energy. And another paper that emphasized the important role of the Hund's coupling is this paper by Christian Howley and colloquia, who actually emphasized the importance of the Hund's coupling in the context of pnictides. And it's really all this same physics which is going on here. Okay, so before I go to real materials, which will come, I would like to give you more analytical insight into these two antagonistic phenomena. Okay, so the way the critical U varies and the way the coherence scale varies. So let's start with the gap and the critical U. So that can be done very, very simply. I can just look at the isolated atom. So I take the atomic limit of my model, and I look at the states, and I do good closed quantum mechanics. I classify the states by the three quantum numbers, charge, spin, and isospin. Okay, and I look at them, and you see that we have a charge 1, charge 2, charge 3 sector, and we can actually calculate the gap of the isolated atom as the difference between the ionization and the affinity, right? So this would be En plus 1 plus En minus 1 minus 2 En. And the key point is that the energies of these states are of course affected, except when there is 0 and 1 electron, obviously, by the Hund's coupling. Okay, so in turn, these transitions energies are also affected by the Hund's coupling very strongly. And bear in mind that this is true even if you consider the case of only 1 electron, because the gap is determined by the transition energy to 2 electrons, which is sensitive to the Hund's coupling. Okay, so if you just plug in these numbers here into the formula for the gap, you will find that for a half-filled shell, this atomic isolated atom energy is U plus 2J, but for all the other cases, it's U minus 3J. Okay? So this is the reason for what I was talking about. If you now say, okay, the transition will happen when this energy is of the order of the bandwidth, and that's the simplest Morse-Hubbard argument you can get, you immediately see that at half-filling, the critical U would be a bandwidth minus 2J, while away from half-filling, the critical point is some bandwidth plus 3J. Okay? So that's the effect I was talking about on the critical U. Okay. So now let me go into the more subtle part of the story, which is the lowering of the coherence scale within the metallic state. Okay. So to understand that, we have to be a little more many-body people. Okay. And we have to think not only of the isolated atom, but how the low energy, the ground state multiplet of this isolated atom will be screened by the other conduction electrons. So what I'm trying to say here is that this lowering of the coherence scale due to the Hund's coupling can already be understood very well at the level of single impurity Kondo physics. And actually, since we are talking about Kondo physics, not surprisingly, this effect was actually discussed in the context of Kondo systems by a bunch of distinguished Japanese colleagues, okay, back in the 70s. So what these people did is they considered the effect of the Kondo, of the Hund's coupling on multi-orbital Kondo models, and they did find that the Kondo scale is strongly suppressed by the Hund's coupling. This can be explained very nicely, and there is a recent paper by Nevidomsky and Coleman that does that very nicely in a very simple toy model, and I can explain this toy model here. Let's imagine we have n spin half impurities, okay? And we lock them together into a spin n over 2, a big spin n over 2 through a Hund's coupling J. So that would be the Hund's coupling J. But apart from this term, this would be n independent copies of the Kondo model. So we have a conduction electron bath, which has also n channels, okay? And each of the channels screens independently one of these Kondo spins. This would be n copies of the Kondo model, which would have a certain Kondo temperature Tk0, okay? But now I'm actually trying to bind this into a big spin, which is a composite object of n spin half. Okay, and I can ask, what is the combo temperature of this problem when J becomes large and you really have to bind the spin S and not individually each spin half? Okay, so you can work this out even with Pullman scaling, okay, and you will find out that the combo temperature of that problem is the original combo temperature of each of these individual combo problems times a very small factor, tk naught over bandwidth, to the power n minus 1. Okay? So you see that there is a huge suppression, actually an exponential suppression of the combo scale, which is due to this Hund's coupling. Okay? So this is basically the physics of the reduction of the coherent scale from the simple screening of each of these individual spins. Okay, very good. So we can be more sophisticated and deal with this problem using the standard tools, numerical normalization group, for example. And these are such plots where you see how the resonance, the Kondo resonance goes from quite broad value here for the choice of parameters that were chosen for this calculation to a very, very tiny value when you actually increase the Hund's coupling here to quite, already realistic values, J over U equal 1/10. Okay, this is another thing documenting how this happens as a function of energy scale or temperature. So you see that we can push this combo scale to really low values using this Hund's coupling business. Okay. So now that I've given you analytical insights into the basics of what's going on, I would like to go back to sort of real materials. And first I'll do that in some sort of qualitative way, and then I will turn on the machinery that was developed in the past decade or so, namely making DMFT realistic, and I will show you what we can do on real materials documenting these qualitative ideas. Okay. So now it's the same plot that I showed you before, but here I've just put on this map some materials. And I've done that not doing very sophisticated calculations, just doing it with qualitative thinking. Okay? So let's take a simple material like strontium VO3, which is a well-known cubic perovskite with one electron in the D shell. So we have a T2G manifold of bands, and we have one electron in this T2G manifold. Okay? And it's been intensively studied experimentally and also by all sorts of theories, and especially DMFT, and everybody agrees that this material is a sort of correlated metal in the intermediate correlation regime with a quasi-particle renormalization of about 0.5. Okay? So the claim here is that this is so because the Hund's rule reduced the critical U. Actually, we can do that on our computer. We can run strontium VO3 with LDA plus DMFT and turn the Hund's coupling to 0, and this would be almost an insulator. Okay? So this is nice. It means we already understand something. So we would place this material here in the sort of darkish region of moderately correlated metals. Okay? Then we can follow this trend and go to the half-filled shell. Strontium manganese O3, 3 electrons in the D shell, and this metal is well known to be a good insulator. It's an antiferromagnetic insulator with an L temperature of about 250 K. We will come back later in the talk. And you see that this material actually is quite deeply into the black bar here, which is the insulating region, and one doesn't need to invoke a larger U or a smaller bandwidth to explain that. This is entirely the doing of the Hund's coupling that has actually reduced the critical U tremendously. Okay? And in fact, it's a fact of life that, as far as I know, there are basically no 3D transition metal oxides of 3D elements with a half-filled shell that are metallic. I don't know any. Okay. And I believe this is the reason. Okay. And this morning you heard a talk by Professor Rao on strontium chromium O3, and this guy has been very, very little studied. Okay. Following the set of arguments I gave you, even though we are working on this material and haven't completed the calculations, I would place it here in the very bad metal region. And in fact, if you look at the very few papers that exist on this material, probably Rao is writing more, but right now there are just a few, and some papers find it insulating, some others find it metallic. It's a very, very dirty, very bad metal. Okay, so this sort of fits with this picture. Okay. Now if you go to the 4D series of transition metal oxides, you know, these materials have typically much smaller U, of about 2.5 eV typically, and they have bandwidth which is slightly bigger because the 4D orbitals are fatter. Okay, so they belong to a different family here. Okay, so you see, for example, that the molybdenum oxide, okay, lie deep here into the very good metal region, and actually it is an amazingly good conductor for an oxide. Okay, while the ruthenium oxide, you would think, have sort of a symmetric situation because they have 4 electrons in the D shell. This guy has 2, and actually you see here I've placed them here in the bad metal correlated regime, and at the end of the talk I will explain why I'm doing this. Okay, so this sort of plot allows to charter, to make a chart of at least some of the oxides of the early series, and to orient yourself, and you see that the Hund's coupling is playing a very important role in this. Otherwise these black bars would be completely inverted, right? This would be here and this would be there. Okay, and in fact, with all its intuition and its empirical knowledge from photoemission and so on, Atsushi Fujimori has in various places, and in particular in his famous review article, such a chart, right? And you see that such a chart has exactly these lobes like I was drawing it, right? With the D3 being the most prone to insulating behavior, okay? And this is very well in line with what's plotted here, okay? And the Hund's coupling is very important for this. Okay, so if you look at this plot, you see that here there are some interesting materials which lie at the tip, according to us, of this insulating region. And at this stage you could tell me, well, nobody is ever going to study these materials because technetium is radioactive. Well, but that's actually not true. There are labs that know how to do that. And I'm going to tell you about, in the last part of the talk, or at least in the, well, now, more or less, I'm going to tell you about some story about these technetium oxides. Okay, but before I do that, let me explain a bit about the theoretical methods that we are using here. I have a reason to do that, which is that this theoretical method, which is dynamical mean field theory, was actually elaborated precisely during the year where I overlapped with Rama in Princeton exactly 20 years ago, more or less. So here we have to handle a problem in which we want to understand metals, so of course we need to describe how electrons hop from one side to the other. We need to handle itinerant aspects. But as I explained to you, the way individual atomic multiplets are screened by the remaining of the system is actually playing a very important role, okay? So we cannot be content with just electron gases pictures. We need to do a good job on the multiplet structure of the atom, okay? And this is exactly what dynamical mean field theory does. It sort of marries together itinerant aspects and atomic physics by basically embedding so the cartoon would be this. It basically replaces a lattice of atoms by one atom in an effective medium in a self-consistent way. Okay? This is just describing this approach with my bare hands. My sort of hand-waving cartoon of this is basically thinking of a material in terms of atoms which are self-consistently embedded in the medium. And you see that's really key to understanding the screening of these atomic multiplets in the context of these oxide materials. Okay, so this was elaborated, as I said, actually in Princeton in 1991, following pioneering work on the large dimensional limit of correlated electrons by Metzner and Volhart. And I would really like to thank Rama very wholeheartedly, because at that time I was a StatMech guy. I was coming from classical StatMech, and I have very little knowledge of quantum condensed matter physics, and the numerous discussions I had in Princeton with Rama during those years sort of at least half converted me into a quantum condensed matter physicist. Okay, so Rama sort of witnessed the beginning of this theoretical construction, and hopefully he will sort of judge that this has come out of age and is alive and well. Okay. Very good. So just to continue a bit on the MFT, I would just like to mention that there's been fantastic progress in very recent years in the capability of handling complex problems with the MFT thanks to algorithmic breakthroughs. And again, there is ETH work there by Philippe Werner in particular, but there are also other people who contributed like Ruptsov and Bell and Parcolet. And this is basically due to the invention of new algorithms, namely continuous time Monte Carlo algorithm, just to sort of summarize these breakthroughs into one single number. When it comes to studying concrete materials with several orbitals using realistic DMFT, we could 7-8 years ago study a material like those down to temperatures of about 1,000 Kelvin. We couldn't go below that. And now, thanks to these new numerical methods, we can actually go all the way down to about 20K or 30K, okay? So this is a huge progress because for strontium glutamate, for example, 20K is more or less the temperature where the T-square Fermi liquid law does apply, okay? So we can go all the way from high temperature down to the Fermi liquid regime thanks to these algorithmic breakthroughs. Okay. Another wonderful thing that has happened in this field already like 10-15 years ago is the possibility of moving from simple models, well, not necessarily so simple, but at least simplified models like the one I described before, to real materials. And there is a whole story behind that, which merges together electronic structure calculations using state-of-the-art DFT and these dynamical mean field constructions. I don't have time to describe this in detail, but I'm going to illustrate the sort of power of these methods on one material, and this material is precisely strontium technetium 03 that I placed at the tip of this insulating domain in my sort of qualitative slide. Okay, so despite the fact that technetium is a radioactive element, actually this material has been recently synthesized and studied in the actinide lab in Karlsruhe by a team of physicists from different places, including Tony Cheatham. And what these people discovered is something quite remarkable. They discovered that this material, despite being a 4D transitional metal oxide, has a nail temperature of 1,000 Kelvin, 750 Celsius. Okay, so incredibly high nail temperature. Okay, so why is that so? If I compare to strontium MnO3, which has the same nominal valence of the D shell, it has a nail temperature which is miserably only 260 K. Okay, so why is this one so much higher? Okay, so if you are a Hubbard model guy like me, okay, you could come up on this issue with a very, very simple idea, okay, which is that we all know that the nail temperature as a function of U, this coupling constant here is basically U. It's actually U plus 2J in this plot, versus U at half filling. Let's say and these materials are half fill. So let's have a very simple notion. You all know that the nail temperature goes from very low values in the itinerant SDW regime to values of order T square over U in very large U strong coupling Heisenberg, and in between there is quite a nice maximum here, okay? And that is when the Heisenberg coupling would grow, but actually the actual nail temperature is still being suppressed by charge fluctuations that are developing, right? And these charge fluctuations, of course, become more and more important as you reach the Mott transition point, okay? So the critical U of the paramagnetic insulator would be somewhere here, precisely in the regime where the nail temperature is maximum, okay? So with these simple qualitative ideas in mind, you would say, okay, that's probably because strontium MnO3 is deep in the localized regime, okay, here, and well described by a Heisenberg model, while perhaps strontium technetium 03 is close to the maximum, which is a sweet spot for magnetism, okay, because it is just on the verge of this delocalization transition. Okay, so we can write a paper about that and say, okay, I'm going to think of these two materials in the Hubbard model language. And probably the referee will complain because this is too simple a sort of picture for such complex materials. But now we know better, and we can study these things with dynamical mean field theory in a realistic electronic structure setting. Okay, for these materials, for the real band structure of these materials, and what we can also do is play with coupling constants. I can take strontium TCO3 electronic structure and play with U and J. Okay? And what happens when I do that is that I obtain these red points here. Okay? So you see, this is strontium TCO3 electronic structure, but I've given myself the liberty of choosing this ratio U plus 2J over U critical at will, and for each of these points, I do an LDA plus DMFT calculations for the full material. And what you see is that, well, the qualitative ideas work quite well. There is actually a maximum of nail temperature here. Okay, you can do the same for strontium MnO3, and you find the same thing. And here, everything has been normalized with respect to maximum T nail. Okay? Fine. So now, what is the realistic value of J and U for those materials? Well, we can actually guess this from a lot of empirical knowledge on the values of screened U's and Hund's coupling that float around, in the lecture on manganese oxide and the papers on 4D transition metal oxides. But we have also methods to actually estimate those things from first principles, doing RPA calculations for realistic electronic structure and calculating the matrix elements of the screen interactions. And when we do that, what we find is that strontium manganese O3 is actually here, okay? So of course these methods are not entirely precise. You may allow for 10% error on the coupling constant, but actually indeed these methods do show that strontium manganese O3 is a well-localized insulator that lies in the Heisenberg regime of this magnetic phase diagram, while strontium technetium O3 is indeed very close to the sweet spot of magnetism. Okay? So this shows you that this blending of DMFT and electronic structure has now reached a stage where we can be essentially predictive, okay? And perhaps not do full material design, but at least help in thinking how to improve materials. For example, this plot goes with a very concrete prediction, okay? Let's imagine we take strontium MnO3 and we apply pressure, okay? So pressure will decrease the bandwidth, so it should move this material in this way. And the nail temperature will increase. And that's well known for strontium MnO3. This has been measured, and there is a so-called Bloch's rule that governs the way T-nail changes. But now, because strontium TCO3 is close to this sweet spot, you see that what should happen when you apply pressure, and actually either tensile or contractive pressure, is that strontium TCO3 nail temperature should not change much. It should strongly violate the so-called Bloch's law. So that has not been measured, and this is a prediction. The nail temperature of strontium TCO3 should be quite insensitive to pressure if this, both this qualitative image and these calculations are correct. How much time do I have? 5 minutes? Okay, good. So I have another story which complements all these ones, which is the story about strontium ruthenate. I will try to summarize it in 3 minutes without entering into the details, and then I will stop. Okay. So strontium ruthenate, and Maurice is not going to contradict me on that, is the helium-3 of correlated oxides. It's the most clean of all oxides. It's quite correlated. Actually, it has effective masses which are not so different from helium-3, incidentally. And every single experiment can be done. When Didi Sama was saying that every experiment has been on nickel sulfide, well, not as many as on strontium ruthenate. You can do fantastic quantum oscillations here, for example. Okay? So everything is known on this material, and despite all this beautiful set of experiments and a lot of very nice theory, including a lot by Maurice, there are still puzzles, and I've tried to summarize the puzzles here. Okay? It's a 4D material, and nevertheless, it has quite strong correlation effects, namely the effective mass enhancement of the XY band, which is the two-dimensional band in this material, is as large as 5. Okay? So it's a strongly correlated 4D transition metal oxide. Furthermore, the most surprising thing is that this large mass enhancement applies to the band which has the largest bandwidth. Okay? So let me explain this very briefly. Here is the band structure of this ruthenium-214. you see this broad band here, which is about almost 4 eV wide. This is the bands that point in the plane, okay, the XY band, which gives the gamma sheet of the Fermi surface. And this is a broad band, which nevertheless has a mass enhancement of 5. These two bands, which are about half as large as broad, have a mass enhancement of 3. Okay, why is that? Okay. So again, we can study this with LDA plus DMFT, and what we find is that very much in line with all the qualitative and model arguments I gave you before, if we actually work out this material with no Hund's coupling, J equal to 0, you will find that because U is so small in this material, which is not at all close to a Mott insulator, okay, then you will find the effective mass enhancement to be small, here 1.7 in our calculation, okay? When you turn on the Hund's coupling, all of a sudden what happens is that this effective mass enhancement becomes much larger, okay? And this is very much in line with what I was saying, namely that the coherence, the quasi-particle coherence scale is strongly suppressed by the Hund's coupling. And at the same time, the two set of orbitals start to differentiate, and indeed the XY orbital acquires larger effective mass, okay? So the Hund's coupling helps making this material correlated. It's one driving force, but why is this mass larger than this one? Okay? So that's another aspect of the effect of the Hund's coupling. Because U minus 3J is now such a small number, okay? U is about 2.3 eV, J about 0.3 eV, something like this. So the inter-orbital interactions, U minus 3J, is really small. So you can really think of each of these three orbitals as being not quite decoupled, but reasonably decoupled. And now we have to look at the individual electronic structure of these orbitals that I probably have somewhere here. Oops. Yes, here, where you see that the XY orbital density of states has the Fermi level very, very close to the Van Hove singularity. Okay? So what I believe is that the reason why ultimately the XY orbital has the largest mass is a Van Hove singularity effect, and actually Morris pointed out long ago the importance of Van Hove singularities for this material. Okay, so I didn't talk at all about iron peptides, and I didn't plan to. I just want to emphasize that in our opinion, there are also Hund's metals to a large extent, and I'll just show you our conclusions. So the main message is that there are other pathways to strong correlations than Mott-Hubbard. You can have metals that are strongly correlated because of the doing of the Hund's coupling, and this applies in particular to the 4D transition metal oxides. Actually, I would go even as far as saying that 3D transition metal oxides are dominated by Mott-Hubbard physics, 4D by Hund's physics, and 5D probably by spin-orbit physics, which would be the topic of another talk. Okay, so that's it.
For anti-ferromagnetic fluctuations, but no long-range order. Is this understandable in your...
Well, it's actually a very good question. I mean, we should, well, the technical answer, which I guess is not really the right physics thing to say, but we should actually calculate chi of Q, okay, and take a look. And that can be done now with these methods, so we should actually do that. I don't have an answer off the top of my head, but I know of the problem. Yeah.
Any other?
Besides having a small Z?
Yes, or a large mass.
Or a large mass. Are there other predictions you would make for the effect of correlations? For example,
yes.
You expect a QE law at high temperatures?
Yes, but that's not so surprising. I mean, that happens in many metals, right? In many correlated metals.
But maybe with a large
But spectroscopy, okay? Spectroscopy is probably a better point. For example, in the iron peptides, in most of these materials, there is no Hubbard bands that is observed, okay? And nevertheless, these are quite correlated metals. A Hubbard band has been observed only for iron selenide, which is, in our opinion, has a much larger value of about Hubbard U. So perhaps one could go as far as saying that many of these correlated metals would be correlated in the sense of having a large mass enhancement or small quasi-particle weight, but no definite spectroscopic signals of transition between Hubbard bands, because the Hubbard bands are not necessarily formed so far from the mode transition. So perhaps that's one catch.
One short question. I understand that Haro available hops.
Yes.
So essentially the energy of the hopping is not just you, but the energy you have to overcome this accessibility. But will that also explain why if I dope this material away from half filling, it still remains to be extremely difficult to make them metallic? Will your approach have any comment to do?
Well, I think the reasons it's the localization of the carriers or the formation of spin polarons, right? Would you agree with that? It's actually in practice harder to dope the half-filled shells than the other ones. Okay. So I don't have an explanation for this right away. Okay. Good point.
I was just wondering whether there is a connection between what Didi talked about a little while ago and what you are saying now. I mean, maybe it is already, you have already said that, but I didn't get it.
You mean about nickel sulfide? Do you think there is a connection, Didi? Okay, maybe that's the answer.
I don't see a reduction of the 5 kilometers to the P2G through orbitals in
Right. I mean, in principle, this is something you should not do. I fully agree. And at P2G set of orbitals. So that's not a limitation for our methods, right? We can actually construct an effective Hamiltonian for a very large energy window, including all the d states and the oxygens, if you wish. And this will be much more reassuring because you have very localized atomic value functions in this case. Okay? So, the technically, you mean? Yeah, you just choose your energy window to be larger. Right. See, instead of